So, Chernoff bounds are obtained Chernoff bounds for a random variable x are obtained by applying Markov's inequality to x is the random variable. As I said, you can define a function over a random variable. That is also a random variable. So, here the new random variable that I create out of x is e to the power of tx. So, this well chosen value is now how good your Chernoff bound is basically would depend on how well you choose the value of t. Now, think of this in the following way. What are my tail inequalities? I want to make a statement like this, that say x is away from its expectation by certain quantity this is some value, some small value. So, this is what tail inequalities are. So, what is this telling you? That say for example, you have this expectation for this random, so your expectation is a real value and these are real valued random variables. So, this x minus ex, so this is just one side, you can if you take mod, then it is like considering x is on both sides. So, let x be just greater than 0. So, what I am saying is, so x minus ex is so say for example, you are looking at the distribution in the following way. So, what I am looking at is x is somewhere here and this x minus ex is greater than a certain quantity. So, this is this certain quantity, right. This probability I want to, it is an upper bound on the probability, right. So, obviously always my goal is to bring down that upper bound as much as I can, right. I want to have a low probability. So, that means when you want to make such statements out of a random process that you are evaluating, you want this probability to be low and you have to choose this quantity. This is also in your hand. We would see examples. This will be in your hand, right. So, you fix certain quantity there. Now, this would have a bearing, because the distribution actually determines what is the value of x away from its expectation, right. So, if you have a distribution, then once you fix the value of the random variable, you get a probability value, right. So, that is a distribution for you. Now, all of you probably would be knowing normal, right. So, normal, how do you parameterize normal? Two parameters, right, the mean and the variance. And then you have this theory which tells you that most of the probability mass is centered around 3 sigma, you know this 3 sigma limits, right. So, this is mu plus minus 3 sigma. So, if you look into your standard normal tables and you kind of find out the area under the curve between mu minus 3 sigma and mu plus 3 sigma. So, you have most of your probability mass there. My drawing is a bit bad, but you understand. Say somewhere is your 3 sigma limits. So, these are your tails, very small tails. Normal has kind of tells you that most of the mass is concentrated around this plus minus 3 sigma. So, that is why these things are known as tail inequalities, where I want to give bounds on probability mass away from the expectation. Fine. And this well chosen value of t actually determines this value of the probability, and which is again dependent on the quantity by which you want to say that. Now, think of this in terms of normal, right. You said that most of the probability mass is centered around this mu plus minus 3 sigma limit. So, that means you chose this quantity. The moment you chose that quantity, this value of the probability is fixed. So, you now know that 99% of the mass or 99 point something something mass lies within this plus minus 3 sigma limit. So, this quantity and this quantity has interrelations. So, sometimes your application should be such that this value of the probability, that this upper bound, you have to fix to certain thing. Then that would drive this quantity. Now, distributions are not amenable to your wishes. Distributions are the way they are, right. They have some predetermined values. On such predetermined values, you are trying to make such statements. So, do not expect that you can fix whatever quantity you like and whatever probability value you like. These two are kind of interdependent, and the probability distribution actually drives them. Okay, that's too much of a storytelling. Let's get to basic mathematics. Okay, so what we use is something called Professor, this session goes till, oh, he is not there, 4:45. Okay. So, we use a thing called moment generating function. So, in the morning I told you that if you know all the moments of a random variable, you know the distribution that random variable follows. So, what we will try to do is, we will try to get a particular function of a random variable from which we can generate all moments of that random variable. So, those kind of functions are known as moment generating functions. Okay. So, this is that t, well chosen value of t, which we will choose later on. So, I parameterize it using this value t. This is equals to e to the power of tx, expectation of that. There are reasons of choosing e to the power of x. If you differentiate e to the power of x, what do you get? That is one of the reasons. Okay, my claim is I'll make this statement, but this statement actually works under a particular condition, which for most of the cases that we would handle holds. So, I will not explicitly get into that. So, let me just kind of brush that under the carpet and say this, that so what is this quantity? As I said, this theorem works under certain cases, but for most of the cases that we will handle, that case holds. So, I am not explicitly going into that. So, just a caveat that this theorem does not hold for all cases, but for you let me not get into that. Proof. So, let us look at the nth derivative of this. This would evaluate to, you are differentiating e to the power of tx in terms of t, right. So, x comes down, it comes down n times e to the power of tx, right. Actually, you can do this when you can swap the differentiation and expectation. So, you remember that linearity of expectation is what? That you could take the summation sign from inside to outside, right. Expectation of summation of xi's, linearity of expectation allowed you to write it as sum of exi's. So, here also I am doing differentiation of an expression that has expectation in it. So, for most functions what you can do is get the differentiation inside the expectation, right. So, I could write this only for those functions. So, that is actually the caveat that I was mentioning. Anyway, so let us get into that, and so now evaluate this at t equals to 0. What do you get? What do you get? And this is the nth moment of the random variable x, right. Now, see, those of you who have learned at least a serious course on probability, well, I mean this theorem holds under the, so you can differentiate around t equals to 0. Okay, so those of you who have done a kind of a serious course, undergraduate course in probability, you must have done the following things. Say for example, I have a random variable x1 that follows binomial with say parameter n1p and a random variable x2 following binomial with parameter n2p, then you know that x1 plus x2 follows binomial with n1 plus n2p. So, similarly, you know for sums of random variables following Poisson, normal, parameters change, but the distribution remains same. Well, can you tell me one example where a random variable follows a certain distribution? Say x1 is a random variable following a certain distribution, x2 is another random variable following another distribution, but x1 plus x2 does not follow the same distribution. Yeah, that can be one. So, think of uniform distribution. So, x1 is uniformly distributed in 0, 1, x2 is also uniformly distributed in 0, 1. Then x plus 1 plus x1 plus x2 is surely not going to be uniformly distributed within 0 and 1, because its range is already, you understand, is between 0 and 2, right. It kind of looks like a curve like this, it is not no more uniform. Fine. So, how do you actually derive new distributions? One way is to go via moment generating functions. Say for example, as we have now evaluated, because of this theory that moment generating function can generate all moments of a distribution, and I have told you in the morning that if you can generate all moments of a distribution, you know the distribution. So, what you can do is get the moment generating function of x1, get the moment generating function of x2, add them up if they are independent, right, and then look into the new distribution, get its moment generating function. If these two moment generating functions are same, then you know that these two distributions are same, right. So, this is one idea of checking whether two distributions are same or not. Evaluate the moment generating functions, if they match, you are done. So, maybe you can do an exercise. So, do this following exercise. Look at a random variable x that follows geometric with a parameter p. You can, by earlier known techniques of finding expectation and variance, you can figure out the expectation and variance, right. By this method that I just showed you, what you can do is, for a random variable having this following geometric with a parameter p, you can figure out its moment generating function, right. Once you can get the moment generating function, get its first and second derivatives. From there, evaluate its first moment and second moment and see if these two values are matching. You would see that they would match, right. So, did you understand this exercise? Yeah, fine. Right. To stay on with moment generating functions, I will do a few more things. Proof is easy. What is this by definition? I will use the basic definition, right? So, this is expectation of e to the power of t into, so this is by definition. Done? Done? Just expanding it. Now, in the morning what we have learned? That if two random variables are independent, then fx and gy are also independent. So, e to the power of tx and e to the power of ty are also independent. And if I take the product of two independent random variables and take their expectation, I can distribute the products. Fine. So, I can write this as e to the power of tx into e to the power of the first term is by definition mxt, the second term is by definition okay. So, you can obviously generalize it to n number of random variables. So, that means the moment generating function of a sum of random variables turns out to be the product of their individual moment generating functions. Fine. I think now I have enough material to do Chernoffs. Okay. Any questions till now? Oh, sorry, I should write it as TA. Yeah. Agreed? You agree to this? So, whatever x might be, e to the power of tx is greater than 0, right? So, this is fit for Markov. Agreed? Now you understand why I defined moment generating functions earlier. What is the above thing called? Numerator? No, not denominator. I keep forgetting, I keep confusing between these two. Fraction above 1 you call to be numerator, fine. So, the numerator is nothing but the moment generating function. And that is the reason we defined this moment generating functions. Okay. Now, what is Chernoff bound about? As I said, to figure out a very well chosen T, right. So, how should you choose your T here? See, you want an upper bound, right? An upper bound as tight as possible. So, you would obviously want to minimize this expression such that t is greater than 0. For t greater than 0, minimize it as much as you can, and then you would get a tight bound. Fine. Right, these are your Chernoff bounds. This is the general form of Chernoff bound. What we would show that is for sum of Poisson trials, Chernoff bounds has a nice expression. So, any queries till now? As I said, both Chebyshev and Chernoff are nothing but Markov applied in a particular setting. So, what we would be more specifically interested in, where did this happen? So, what are Poisson trials? These are 0, 1 independent random variables. Your Bernoulli trials, whose sum was this binomial, are basically IID Poisson trials. So, that means for Poisson trials, each random variable can have different probabilities. In Bernoulli trials, you have the same probability, right. So, in here we will be dealing with Poisson trials. So, I will have a bunch of 0, 1 random variables. Each one, say the xith random variable will have a probability, say pi. That is the setting, right. So, I have these are 0, 1 independent random variables Poisson trials, and this has a probability p1, p2, pn. By this I mean that probability of x1 equals to 1 is p1, probability of x2 equals to 1 is p2, so on and so forth. So, that means probability of xi equals to 1 is pi. So, this probability is different. If they are same, then we call that to be a Bernoulli trial. Okay. So, now I look at the sum of these Poisson trials. Okay. Now, let us figure out quickly a few things. What is expectation of x? Sum of all pi's, right? Let me call that to be mu. Okay. Now, for a given delta, so this kind of bounds we want interested. So, where x is a sum of independent Poisson trials. Right. Okay. So, mind you, to apply Chernoff bounds, what I need is this thing. Now, my x is a sum of independent Poisson trials. X is summation xi. So, if it is e to the power of summation xi, that means you can do product of e to the power of xi, and your xi's are zeros and ones, easy to handle, right. So, now let us get going with this moment generating function. Yeah, quickly figure this out. So, this is nothing but expectation of e to the power of t xi. Xi is 0 or 1. So, what I get is pi into e to the power of t plus 1 minus pi. Agreed? So, you are okay with this expression? Now, do a little bit of algebra, simplification. So, get 1 out, 1 plus pi into e to the power of t minus 1. This I can write as e to the power of pi into e to the power of t minus 1. Why? Because for any y, you can write this, right? Because if you expand e to the power of y, you get 1 plus y square by 2 factorial, so on and so forth. So, I am just neglecting the higher terms. So, this is the moment generating function of each xi. I now know that x is summation of xi. So, quickly figure out what is moment generating function of xt. So, apply that earlier theorem which divides the sum to products. I have already deduced each one of them. So, product of this is e to the power of e to the power of pi e to the power of t minus 1. Done? So, this exp means actually this e to the power of summation pi already we know to be equals to mu. So, I have been able to figure out the moment generating function of the sum of the Poisson trials. Right. Now, coming to the final theorem. Oh, sorry, I think there will be a minus here. Okay, let's now try to prove them. Now, remember, Chernoff bound is nothing but Markov's applied to this. My capital X is now the sum of 0, 1 independent Poisson trials. I know its moment generating function. I have to now suitably choose a t. That is what remains. Okay, so, I do one for you, and by the way, I mean, Chernoff bound actually comes in very many different variants. It is like here I am just saying that x is greater than equal to 1 plus delta mu. You can make statements like x minus ex, mod is greater than something. So, you can make many kinds of statements, right. So, you have suitably different Chernoff bounds for each one of them. So, we will put some of them up on the tutorial sheet. So, what I do is I prove this one for you and leave the rest for you to do, because if you get the essence of one, the rest are just doing the calculus in a little bit different way, otherwise the philosophy remains the same. Okay. So, this theory actually tells you that if need be for your own particular case, you can derive your own Chernoff bounds that fit your particular application, and people do it. Maybe it's like right. This is what Markov is for you. Okay. Now, I have already deduced this one. This is already done. Right. E to the power of t minus 1 mu. Replace that. Now, choose your t suitably. Now, for any delta greater than 0, you see, a good choice of t is a logarithmic function. because e to the power of log n is right. That is the reason. And this is obviously greater than 0. So, this is what I set out to prove. What did I need? Moment generating functions. The fact that if I am dealing with sum of independent random variables, the moment generating function of the sum is equivalent to the product of the individual moment generating functions. That allowed me to figure out the moment generating function of x, which was the sum of 0, 1 independent random Poisson trials, and then it is just choosing a t, particular t. Now, for some cases, like in here, it is like what I set out to prove allowed me to set t to be some log 1 plus delta, and things were nicely fitting in. There would be cases where you have to do calculus, because there was that minimization expression, right. So, that means you have to do a derivative in terms of t in some cases. So, that depends on the form of the Chernoff bound. So, I will put up some more forms for which just setting a t to log of 1 plus delta might not help. You might have to do a little bit of more calculus. Okay. So, there are two forms, remember, two forms. I have proved the first one for you, second one I leave as an exercise, and I will give you some more forms of Chernoff bounds, which again can be proved similarly. Same setting, meaning n 0 1 independent Poisson trials. Prove that for 0 delta less than equals to 1, probability x greater than equals to. So, you are varying delta in particular ranges. উদ্দালক এগুলোকে একটু এক্সারসাইজে ঢুকুন। So, as I told you, Chernoff bounds or Hoeffding bounds, they come in different formats, and which one you choose actually depends on the application that you are handling. So, whenever like we researchers have to use Chernoff bounds, we have to, from a big repertoire of Chernoff bounds, we have to suitably choose which one to use, and that would obviously depend on the application in hand. So, these are kind of very popular ones. So, that is the reason I did this. Okay. So, we will do a corollary of this theorem, and then again go back to the same example we did in the morning. So, this corollary also has the same setting. Now, this corollary will actually follow the corollary that I wrote. So, it is x minus mu mod greater than equal to mu delta, right. This would actually follow from this 1 and 2. Why? It is easy to see that for the first term you can rewrite it as x greater than equal to mu plus mu delta, right. X greater than equal to mu plus mu delta, bring mu to the other side. So, you have x minus mu greater than equal to mu delta. Similarly, for the lower end, lower one, number 2, you will have x less than equals to mu minus mu delta, bring mu to the other side, x minus mu is less than equals to minus mu delta, fine. Now, if you now look into both of them and you can bring them together with the use of a mod sign, right, and then the mass on this right hand side gets added up, fine. So, what you are doing is, earlier your x was following only one, now you make your x follow both of them. So, now the range increases, right. So, you are also adding up the right hand side, that actually makes it 2 in here, fine. Again, this is an exercise which you should try. Fine. So, this is like now in a nice form that we know that for a random variable x, how far it is distributed away from its expectation by a certain quantity, and I have this probability value. Now, this now look at, if you look into the probability value, it is e to the power of minus something. So, that is appreciably a low value, right. So, it is a negative exponential. Let us now apply it to our morning example. Remember the morning example? Let us get back. So, from Markov what we got, that x greater than equals to 3n by 4 had a probability of 2/3. There was appreciable improvement in Chernoff, it was almost a 1 by n inverse polynomial. Let us see what Chernoff gives us. Again, this capital X, what was it? N independent tosses of a unbiased coin, right. So, this is a setting of Poisson, right. Each one has a probability of now half. It is more than Poisson, it is binomial, it is actually Bernoulli trials, because each probability is same. So, the number of heads you can look at as sum of xi's. So, this setting of n coin tosses of an unbiased coin, and where each toss is the outcome of each toss is independent of all the previous tosses, is also a setting of sum of Poisson trials. All of you agree to that? So, that means it is also a fit case for application of Chernoff bound. Now, remember this, Markov you can apply almost anywhere. If you can just figure out the first moment, the expectation Markov gives you certain result. Chebyshev is a little more difficult to apply because you need the variance. Chernoff is even more difficult to apply. Why? Because this complex event, which is modeled by the random variable capital X, you have to write it down as a sum of 0, 1 independent random variables. That is not always very easy. But if you can, then that is a fit case for Chernoff. So, in here it is a fit case for Chernoff. So, let us apply Chernoff and see if you can even get more than 4 by n. Okay, as I told you, which form of Chernoff would I use actually depends on the judicious choice of the designer. So, I will choose this one. X minus mu, right? So, mu for our case is, mu for our case is n by 2. What is mu? Udalog, you have confused them with that probabilistic method. X is sum of xi's. This is half. So, expectation of xi is half. So, expectation of x is okay. So, x minus n by 2. So, remember that deduction in Chebyshev. So, how I brought down this x greater than equal to 3n by 4 to this format, right? Same thing. Now, just figure out what is your delta. Your mu delta is equals to n by 4, your mu is n by 2, that means your delta is half, and that means your delta square is 1 by 4. So, this is 2 to the power of 2 into e to the power of minus 1/3 this term, mu is n by 2 and delta square is 1 by 4. So, this gives you an expression like 2 into e to the power of minus n by 24. So, you understand the sharp fall. Markov gave you 2/3, Chebyshev gave you 4 by n, 1 by a polynomial, and this is giving you a 1 by an exponential, right? You all already know that an exponential grows faster than a polynomial. So, constant, constant, polynomial is a greater function than that, exponential is a greater function than that, but I am looking at 1 by each one of them, right. So, 1 by an exponential is less than a 1 by a polynomial. So, Chernoff is obviously giving me a much better bound, it is giving me inverse exponential. Okay. Now, as I told you at the very beginning that you can play around those things, right, this quantity that you want to say and the values. Let us look at one such example and try to understand its meaning and then end. Delta square, right. So, 6 log n by n, this is equals to 2 by n. Now, see, why did I choose such an expression? So, what I wanted to show to you was, mind you, Chebyshev gave you a bound like 4 by n, remember? Chebyshev gave you a bound of 4 by n, where, just look into the Chebyshev setting. So, I have given you a bound where Chernoff is giving you a probability bound which is comparable to what Chebyshev had given you, but there is a big hole in there, right. So, Chebyshev had given this to you for x greater than 3n by 4, or to put it in terms of the expectation, x minus n by 2, where n by 2 is the expectation. So, the random variable x taking value away from its expectation greater than equal to n by 4, this is a very large quantity, right. It required n by 4 to give you a probability of 4 by n. Now, look at what Chernoff is doing. To give you a probability of 2 by n which is comparable to 4 by n, the range it is allowing you to play with is very small, it is square root n almost, there is a log n correction term, which was earlier linear, now has become sublinear, right. Square root n, you have come down by that much. Earlier, Chebyshev to give you 4 by n was allowing you a range of n by 4, but Chernoff is giving you that almost comparable value where the range is very small. Mind you, I am playing with the same random experiment, my setting is just the same, n independent coin tosses of an unbiased coin, same setting, but see what the story that Chernoff is telling you and what Chebyshev is telling you, right. This quantity, this is sublinear in n, right. So, log n, square root n, these are functions which are much below n, they grow. So, n grows much faster than square root n, right. So, Chebyshev is giving, Chernoff is giving you a almost comparable probability bound by making x stay very close to its expectation, right? X minus n by 2, that is the expectation. So, you are saying that the random variable taking value away from expectation by that much. Now, that much, this square root term is much below n by 4. It is a function much less than n by 4. So, Chernoff is actually giving you a sharper bound. If you had allowed it the range of Chebyshev, it would give you an inverse exponential. But if you want the same probability out of Chernoff, then it can squeeze the range. Now, this is telling you that the random variable is really concentrated around its expectation. As I said, I want to say that a random variable x follows a nice distribution. By that I mean that with high probability it stays close to its expectation. By how much? That is that quantity. What is that probability? This is the probability. Mind you, I started by saying that you can play around with the values and the probabilities. I showed to you one such game, and you can kind of play around with these values to get newer kind of bounds. So, I would stop here. If you have questions, I will take it.